much more robust quantum algorithm implementation, right? So at this point, I would like to stop this talk and take some examples of quantum algorithms. So So every there is a huge scope to develop practically realizable quantum algorithms because, as I mentioned in my the talks earlier talks, that there are difficulties in implementing gate operations, large number of gate operations, because of system errors and various other things. So let's see what is the current status of algorithms and what have been done in the limited systems, right? In addition to what I showed, what we have done in our lab with 2, 3, 4, and 6 qubit. So there are a few other things. So there are many well-known algorithms. Right? People always just talk about two things: Shor's algorithm and Grover's algorithm as famous, and has there been any other algorithms? Now that's a wrong understanding because there has been a lot of algorithms which have been developed over last few years. Just because they are not trying to solve a well-known or very obvious layman understandable problems, people don't see them as a very effective. But let's say phase estimation, quantum phase estimation is considered as one of the most efficient base protocol, like a base algorithm. Using quantum phase estimation, you can actually implement many quantum algorithms. You can actually solve many mathematical problems. Similarly, quantum Fourier transform also has some quantum phase estimation associated with it, and that also helps you to identify eigenvalues and find them as a solutions very efficiently. And these are part of Shor's algorithm. Like Shor's algorithm is a configuration of various substeps which factorizes even the big problem, and these algorithms become part of it. And I did discuss about Grover's algorithm in my yesterday's class. Just like Grover's algorithm, there are other algorithms which all involve amplitude amplifications. They are also quite important. There is Dodge-Joshua algorithm, which was one of the earlier algorithms. I mentioned about David Dodge, who was somebody who initially came up with a promise of quantum computers for computational perspective. And the algorithm which he had developed was something which is also quite famous, the Shor's algorithm. And there are other algorithms which you call Brownstein-Wagerani algorithm. There is variational quantum eigensolver algorithm, which tries to solve some optimization problems. It's a combination of quantum and classical algorithm together, and that's been very popular these days because of the limitations of the hardware. Quantum hardware, people use combination of quantum system and the classical system to solve some of the problems more efficiently. Solving set of linear equations is considered as one of the important problems in a computational language, and there are quite popular HHL algorithms and algorithms associated with it, which does solve combinations of linear equations more efficiently than the classical system. However, the hardwares we currently have are not capable of efficiently implementing any of these algorithms in a large qubit system. When I say large qubit, which means that I'm talking about like 20, 30. There has been few tens of hundreds of even 100 qubits have been claimed by some big IBM quantum processor, but they have not been able to implement any of these algorithms at that large number of qubits which they have, because the number of gate operations needed are still very high. But at a small scale, like few qubits, all these algorithms have been implemented and tested quite efficiently. Right? So only a small scale demonstration has been done, has been reported. So what we call as an algorithm, or what we simply call as a computing mathematical function on a quantum computer, right? So in order to design quantum algorithm, we need to know the function you have to execute. And that function should always be like some binary operations only, right? Because binary operations which can involve superposition. The classical computers would only involve just 0 and 1, but the operations would involve superposition. So it means that if I have some input state 0 or 1, there is a function which will still give me an output 0 and 1 in some superposition configuration. Now for that we need to design a quantum circuit that that consists of many gate operations on it. So this Dosh algorithm, I'll just give one example of an algorithm in a slightly extended form. The rest of them will be just briefly discussed. A Dosh algorithm tries to identify some very unique problem. For example, there's a balance function or a constant function. So now constant function, which means that a given output is always the same, that they don't have two different values. A balanced function would have 0 and 1 equally, and that's what we call as a balanced function. So if I'm giving you some output, how much information is needed for me efficiently to say whether the given function is balanced or not, right? Ideally what it says is that if I'm giving you 2 bits and then please say whether they are balanced or not, right? Or a function particularly, right? So whether the function is balanced, it's okay, sorry, it's about operation, right? So whether the output is going to tell me anything about the function is the first question here. So f of x is an operation which can give me an output which is different to my input, or f of x can give me an output which is same as my input, right? So that's also, there are multiple possibilities here. So what we see here is there's a function f of x. F of x will give me an output 0. If my x is equal to 0, it will give me an output 0. If my x is equal to 1, then also it will give me an output 0, which means that irrespective of the value of x I am giving, my output is always 0. It's the same case in the second one. Irrespective of my value being 0 or 1, input is being 0 or 1, my output is always 1. So now these two are considered as a balanced function. Now if I get this output, I would say my f of x is balanced. If I get this output, like which is different, then I would say my function which has been given to me is balanced function. But to identify whether there's a balanced function, whether the given function is a balanced or not balanced, I need to always give 2 inputs. Only if I'm giving 2 inputs for x and y, I can get an output. So I need to make queries twice, right? 2 times I need to ask this question. First time I should give 0, I should make a measurement. Second time I should give 1, I should make a measurement. Only then I can infer whether it's a balanced or a constant function. So if I have a large sequence like this, then I need to do at least equal number of times to show whether they are balanced or function. So can quantum computers do this using superposition more efficiently is the first question. It might look very simple and trivial, but it highlights the role of superposition in a quantum. So we want to find whether the particular function with 0 input bit and 1 output bit is constant or a balanced function, right? It's just that you have 1 input bit and 1 output bit. Using that can be found. Classically, we need to evaluate the function twice, which does not happen. Which does not happen with quantum. We can do it with a single one. That's what we're going to show here, how it can be done, right? So this is a circuit which can do that. So I can take a 2 qubit 0 and 1 as an input state, and say all that I need to do is what this f of x will do, right? I don't have to worry about my input. F of x, whether f of x gives me a balanced output or a constant output is what I need to figure out. So I can begin with some state 0 and 1. I can implement an AND operator. Depending on the x and y output I'm going to get, I can somehow come up with the solution just by measuring on only 1 qubit, right? You don't have to ask query twice. So I send a 2 qubit system, I make 1 query, and immediately I can say whether it is a balanced or a constant function. So complexity is reduced by half straight away. So a simple mathematical expression for this circuit is given below. My psi1, which means that after implementing 2 AND operation, I will end up getting these 4 states, right? The 4 basis states. So now what we are saying is that basis state, so there is a function here. If my output is x in the first qubit, that will be x. But if my output is y in my second qubit, then my function is operated on that, right? That's what it says. So what it is doing here is shown in this figure. If f of x is equal to 0, then psi2, which will take this form, f of x is equal to 1, psi2 will take some form, and f of x is equal to x or x plus 1. In general, it will take this form. So which factorizes as this particular form. So if f(x) is equal to, both of them are equal to 0, then we call them as constant function in this balance. So these, that is, two balanced cases differ only if unobservable global phase exists. So it means that there is a global phase which exists in one of them. So that's when you can look at it, right? So the output of site 2 and site 3 are given here, and the final step, when we measure the first qubit, we can see that the output will always be 0 if the function is constant, and the first qubit's output will be 1 if it is balanced. So all that we did was just make a measurement on the first qubit, and instantaneously I can say my function is constant or balanced, which usually needs a 2 qubits. So all that has been done here is, in this circuit, I have exploited a superposition by applying Hadamard operator, and then that's all. Like, if I'm applying Hadamard operator twice on the first qubit, and if the function was not balanced, the state would have flipped, or else it would remain the same. So if my input is 0, if my output is also 0, then it's balanced, and if it's flipped, then you can say that they're balanced. So this is one of the simple example of the algorithms, and things do get complicated in a similar way, and complicated algorithms are developed based on it. Now there is another simple example here, which is a phase estimation. I'm not going into the detail of phase estimation, but at a single qubit level, we can simply see what do you mean by phase estimation. Is that I take a superposition state, then top and bottom, there are two possible ways of generating having a superposition state. Now for this state, if I apply an Hadamard operator and I make a measurement, I will either get 1 or 0 depending on what is my input state. Now, just by making a measurement on measurement on the photon and identifying whether it is 1 or 0, I can say what was the phase with it, whether there's a plus or minus in that superposition state. So this is a simplest version of phase estimation. On applying an Hadamard, I'm going to rotate my qubit state into a single basis state, and now that basis state is going to tell me what was the phase of that qubit. In a similar way, you can actually take a large number of qubits, and identically you can create this superposition state, and you can make some controlled operations, and you can make estimate the phase of a system. So phase of multi-qubit system efficiently, and that's one of the standard problems which people have been looking at. So, but I will now, with this example, I will go to the state of the art, which means that in last few years, which has been considered as a big considered as a very promising result, which shows the potential of quantum computers. Now, this is a 54 qubit Sycamore chip which Google had used to demonstrate something which they considered at that point as what you call a supremacy, right? So where you can they didn't do any meaningful algorithm, or they didn't implement an algorithm like phase estimation or Shor's or anything, but what they did was they created a complicated just a random circuit, right? Just randomly connect, because what I told in the initial talks was that because of coherence time, there is a limitation on the number of gates you can implement, and because of connectivity, there is also a limitation of what qubits can be connected with another one, right? So now if you see here, this is an architecture of 54 qubit. Now a qubit at one hand here is not directly connected to the qubit here. If I want to do a control knot operation between the qubit here and the qubit at the other end, I need to use all these qubits which are coming in part to do that one operation, which means that just by to entangle my first qubit here and the last qubit here, I need to do a lot of gate operations. So that is what we call a complexity of architecture. Now to implement something more reasonable, they didn't worry about demonstrating any specific problem. They realized that let's make use of the nearest connectivity and just implement gate operations randomly on them, whichever is possible. And what is the maximum number of gate operations you can implement in a given coherence time was the question which they tried to ask. And then they did something like this, right? So you can, this is just one simple example of 1, 2, 3, 4, 5 qubits. In that 5 qubits, you couple them by using this couplers, which is doing some control NOT gate operations between them. And you can see here, these 5 qubits you can always do some operations on each qubit and then controlled coupling between them. You do this control NOT gate operations, and this kind of implements a simple or a random. This is just a random, right? Because it's not solving any specific problem, but it is still creating some random entangled state. So they did generate a state like this for a 54 qubit. Actually, the result was 53 because one of the qubits was not working, and that was marked. And the 53 qubit, which they created some random circuit. And then the question they asked was, if you had to solve or like implement an equivalent state generation on a classical computers, how much resources and time you would need. And what they had said at that point was that no classical computers can efficiently do that in a given time, and we can show with 54 qubit. This also boils down to why I was talking about the power of a good 50 plus qubit system compared to a classical system. But later on, in fact, there were questions which people had tried to raise. There is classical verification, and people came up with a new classical algorithm itself, which can actually reproduce a result with a more reasonable time than what they had estimated. Nevertheless, what it did show was that you can make these 54, 53 qubits connected in some way, some random way, and give some quantum state as an output, even in a noisy system, and show that you can do something reasonable. And if the qubits are very clean, and if you can achieve a better connectivity, then you can do a more efficient algorithm implementation, right? So that's something which was one of the very important results. Now I had this slide earlier, but now this is a simpler version of the same thing, which is version 1 and version 2. They did implement a specific task, that's boson sampling, which is like, you have multiple single photon generation unit, and all these photons are fed into paths, and then you make them all do a boson sampling at every path, and you can measure them as an output, right? So this is another in 2002, 20, and then 2021, the two experiments were done to demonstrate you can efficiently implement a boson sampling on a photonic hardware, which can't be done in other hardwares, and no classical computers can do that efficiently. So these are some of the results which they had shown, which is kind. So that though there are, as I mentioned, there are limitations. Available coherence time is something which is most fundamental limitation which we have today, that result into a short circuit depth, which means that the number of circuit and the connectivity, and limited connectivity, that's resulting in more gate operations to perform. As I showed in one of the earlier slides, where if I want to connect the two qubits which are far away, then I need to implement many gates operations in between, and then every gate operations costs some coherence time and resources, which means that the system becomes noisy even just to make the first and the last qubit connected or entangled. Now that limitation is a big challenge. The quality and number of qubits are still limited to do error corrections also, because errors are prone, and now errors can be operational errors and system errors. If you have a larger number of qubit system, you can always encode information in more qubits, and error corrections can be done more efficiently. However, while hardware technology is being developed and researchers across the world are building more efficient hardware, what people we've been looking at is, and as an academic community are also trying to look at, is to think of simulating some reasonably understood quantum systems on a near-term devices, so that we can validate and exploit it. So at the current due to current limitations, we all have to work towards developing quantum algorithms with short circuit depth and with a limited coherence time, and that's been the focus for the research community, in addition to scaling up to larger number of qubits. And there has been many fundamental and most beautiful demonstrations which has come out with smaller number of qubits. In my last talk, I showed about generating keys using 4 qubit systems, and even doing teleportation using 3-qubit systems in a photonic system, photonic qubits. In a similar way, there are other physical problems which also have been efficiently implemented. One can actually take classical computers and simulate them, but doing it quantum mechanically, just like what Feynman had said, if you are trying to mimic quantum system, please use another quantum system so that you are doing it in real. So that's what was his invitation also, right? So what they and it also validates the theory, because when you are trying to use some other language and it may not be an exact replica of what's happening. So this is what we call an high energy physics problem, where you have particle antiparticle creation, and these are like, it can't be done in a laboratory setup, right? But you can now simulate them using quantum states efficiently. And using a simple 4-qubit system, ionic system, a particle antiparticle creation was developed, and there is a state which was generated, and there is some simple gates equivalent which was implemented on it, and one could show how the coherent dynamics of particle antiparticle creation can be modeled using a quantum computer. Now what it says is that it's a simple particle antiparticle creation, but this gives an invitation for modeling many high energy physics experiment, and then one can actually zero down on the most required or efficient model which has been simulated in quantum computer, and then go for doing a real-time experiment in Large Hadron Collider or something. So the Large Hadron Collider, which is there in Geneva, where people have been, the whole globe of, all the countries have contributed for its establishment, and very serious experiments have been performed in high energy dynamics. But if you have to run those experiments, billions of dollars have to be spent. But if you can simulate them efficiently and zero down the experiments which you have to do, the cost can be reduced significantly. And this has actually been one of the agendas or the focus direction for people working in LHCs these days. And they are trying to see how efficiently they can use quantum computers to model and come up with an optimized versions for experiments designs for them. Right? So because of the limitations of quantum computers today, there is a class of algorithms which we call variation eigensolver algorithms, which takes advantage of the best of the classical computers and the best of the limited quantum computers available today, and do something which is not efficiently doable with just one of them today, right? Either one of them, classical or quantum computers. So what classical computers can do efficiently is that you can calculate Hamiltonian, choose parameter value, and from that you can, after you choose the values you need and input values, then you can run the circuit on a parameterized states, in a multi-qubit states, and then you can then measure those states. You can again run them in a loop, so you can continuously make them run and optimize the solution what you want. Once you are convinced that your state, what you got parameterized output state is effective, you send it back to your classical computers, which evaluates Hamiltonian and then gives you a lowest Hamiltonian expectation, which is called as finding lowest energy of a state. So finding ground state energy of any chemical molecules or complex systems are very, very complicated. So the Hamiltonians which people in quantum chemistry study, or people who are trying to do some molecular dynamics, right? They all write those quantum states and then try to use some approximations to arrive at Hamiltonians or like lower energy states calculations or everything. Now using the combination of classical quantum computers, people have efficiently shown that this is a very promising way in a near-term devices. So similarly, calculating ground state of helium and H plus energy has been demonstrated using photonic system. It's a simple 2-qubit system, nothing more like we described earlier. But instead of taking photons in different degrees of freedom, at that point they had taken 2 photons to realize 2 qubits, and then there was interactions, control not gate operations was done, and then there was an output measurement. This is a quantum processing part, and this is a classical optimization algorithm. So where you do a classical optimization, give an output which controls what should be the parameter for a quantum computer. The combinations of small quantum processor and the classical processor together showed that efficient way of calculating ground state energy of helium ion. And similarly, this has not been efficient. This was something which I had mentioned yesterday, that there are complicated problems like nitrogen fixations, which can't be done with the best of classical computers. But people have now come up with a combination of classical and quantum algorithms which can somehow solve these problems. However, there is still certain limitations of the capacity of quantum computers to do this part also, but that's something which one can actually anticipate to be done in very near term. I don't have to wait for a very long time for larger number of qubits to be ready. So there is whole lot of things are done in a classical computer. You can generate a structure, you can optimize the structure, you can optimize the active spaces, you can even index them efficiently, and after that is what calculating correlated energies, what is like an entanglement, right? Because these are like highly correlated systems, the entanglement representation would be very, very complicated. So now that can be efficiently done in a quantum computer, which would need a huge resource on classical computer. After that, you can transfer them back to a classical computer, and then you can do. So where this is helping us is to reduce the circuit depth which is needed to a very high extent, and also coherence length available. If you have to do everything in a one go on a quantum computer, then it means that there is a cost of coherence time even to do these classical operations, and the number of gate operations also is cost. Now you can minimize them all and really pick what can't be done at a classical computers and implement on them. Of course, this is not been implemented. In a similar way, there has been other, in the interest of time, I also try to run a bit fast. There has been class of algorithms which we call a quantum walk-based algorithms, which also implements many physical systems. So there has been, like as I had also mentioned yesterday, there is a lot of statistical physics models, dynamical models, which has anything to do with dynamics, like movements in the nature, complicated or simplest or chaotic, whatever we can think of. They all can be modeled using a random walk in a simpler and a complicated form configuration. In a similar way, any quantum dynamics which we are going to take in this universe can be modeled using a quantum walk. Now this is just a one dimension. I can take multi-dimensions, I can look at it. So it means that an atom's dynamics or a neutrino oscillations dynamics, many things can be done with it, right? So now this is another algorithm which kind of can be implemented in our system. Right? For example, we call this a continuous time quantum walk algorithm. What it does is that the graph, right? You can consider any graph. You can write a matrix for that. So graph matrix, we call this adjacency matrix, how the graphs are connected. If the edges are connected, I fill this matrix element as 1. If the edges are not connected, I fill them 0. Like for example, there are few examples I'm giving here. 1 to n states, it may like 1, 2, 3, 4. So if you see here, 1 is not connected, like 1 is not connected to, so 1 is connected to 1 is connected to 3 and 1 is connected to 4. So I get 1 and 1. 1 is not connected to itself and 1 is not connected to 2, they are 0. So similarly, 2 is connected to 4 and 2 is connected to 3. So 2 is also connected to 3 and 2 is also connected to 4. So for this, there is this adjacency matrix. For this, there is this adjacency matrix. For the other graph, this. Why is this adjacency matrix very important? Because they actually help us to simulate Hamiltonian. Right? Every dynamics in this universe, we try to model them using an Hamiltonian. What is Hamiltonian? Hamiltonian is a kinetic and potential energy in some particular configuration. Right? I'm not going into detail, but if you know Hamiltonian, which means that you can simulate the dynamics of that system. So I can say, if I know Hamiltonian, then I can say the state at some time t will become state of something at some time t is equal to 2. Right? So I can actually evolve them and look at it. So, but what adjacency, dynamic and the diagonal would try to say is that the connectivity between them, and then how the connectivity will help in transport, right? So I can just define some parameters which you say the Hamiltonian can be defined for it depending on the weight, and I can just with adjacency matrix I can try to calculate, or I can try to mimic an Hamiltonian with it. So now with the adjacency matrix, if I have an Hamiltonian and I try to expand that e to the power of Hamiltonian, is what we call exponential to the Hamiltonian, will be a unitary operator, and you can simulate a dynamics. So this is what it said, the dynamics, so diagonal element minus adjacency would mean that it's helping to model the dynamics. Adjacency will try to tell you the connectivity, but the diagonal minus adjacency will help you to define the dynamics. So the similar way, this tossing a coin, where I can toss a coin, if I get head or tail, I can move to the left or right, and just like the way here, if it's spin up, you move to the left, if it's spin down, you move to the right. I can define a dynamics, and I can give some probability output here, and these are efficient quantum algorithms which have been developed. So what this helps is not just to to look at search or anything. When I said Hamiltonian, which means this is a very famous equation, a relativistic quantum mechanical equation. We call them a Dirac equation. Now there is an Hamiltonian associated with it. There is a mass of this particle, subatomic particle, or what we call a relativistic particle, and there is a speed of light associated with it. Now, if I want to go, and this is what actually Feynman was trying to hint long back, what he was trying to say was that if I have to simulate a quantum computer, quantum state, I need to simulate it on a quantum computer. It's just because if I have to simulate something like this, I need to first break down the problem into some universal or some unitary matrix, because I need to write them in a binary language, convert them into a change of the states. So this is equivalent to some matrix of this form. I'm not going into the details of it, but you can actually see a derivative in time means there's a change, movement in time. It goes from time one particular point to another. So t minus and t plus would be derivative to the left and minus to the right, right? There's shift in position space. So shift in time, and there is a shift in time associated with x together makes this form. So, but we don't have to worry how this is written in this form, but these are available in textbooks. So cellular automata model is what we call. If I see the matrix which people in high energy physics use, we see that there is a diagonal element and off diagonal element. There is a shift associated with them. But off diagonal elements, you don't have any shift associated with it. So what it says is that if I can simulate or implement this matrix, then I can actually implement Dirac equation. So this is every term is associated with a mass and then speed of light, and we can ignore them. But what quantum walk does, the algorithm which was not developed for this straight away, but it was developed from different perspectives, yes, is that it takes this matrix form. If I compare this with the Dirac equation matrix, this off diagonal elements also has three terms, which is absent in my previous slide. Here I don't have an off diagonal element three terms. Now, when somebody who works on algorithms looks at these problems, first questions comes to them is, okay, a quantum walk algorithm does something like this, but a physical systems dynamics has something slightly different. Is there something I can do to change in this algorithm configuration which maps them identically? Then if I can do that, then I have developed an algorithm which can simulate the Dirac equation more efficiently, right? This is the example here. Now this is a quantum walk algorithm, and this is a dynamics of Dirac equation. I have to map this something to equal this. But the simplest one we can always straight away look at is, let me take theta is equal to 0. If I take theta is equal to 0, then all of this term becomes 0. Like sin 0 is equal to 0, and then this also becomes 0. Theta is equal to 0 means your massless Dirac equation. So it means that this term also becomes 0. Both of them will be equivalent to each other. So it means that a quantum walk with theta is equal to 0 in algorithm is equivalent to massless Dirac equation dynamics. So you can simulate anything to do with massless Dirac equation. But what should we do to do massive Dirac equation? And this was a question open to the community, and people did explore them. So the way one understands the quantum walk algorithm is that it takes this path, goes to the left or right, goes to the left or right. But if you're trying to see the relativistic quantum dynamics of which comes from Dirac equation, because of the mass associated with that, there is not just goes to the left and right, there is also mass which pulls it, keeps it at the same place. Now this is something which is making different between quantum walk algorithm and Dirac cellular automata. So I need to modify my quantum walk algorithm such that in addition to going to the left and right, if I try to make them remain at the same position with time, then I have I'll be able to simulate Dirac equation efficiently. And in fact, that reveals some interesting feature which people know in relativistic dynamics, which we call Jitterbug oscillation. So these fine oscillations comes, and this all can be mimicked by an algorithm very efficiently. So as I said, the simple way to see here is that I need to replicate both going to the left and right. So what we can do is that I do a coin operation, go to the left and remain at the same position, and again do a coin operation, go to the right and remain at the same position. If I do this continuously, and I will end up getting a quantum walk operation which is exactly identical to Dirac equation Hamiltonian. Now it might look, oh, why is all this mathematical description to show they are equivalent at all of those things? But these do have an implications to quantum computing algorithms. So what it means that the moment if we show from an algorithmic side that okay, I have got a algorithm which gives me an unitary operator or an operation which is identical to something which is to do with Dirac equation, which means that I can simulate anything to do with the Dirac equation using this algorithm. The moment it is shown, it becomes a problem of interest to implement on a quantum computer. So now all that would be needed is that we should break down these unitary operators. Because this is a unitary operator, I need to break them down into set of gate operations, right? So which are poly operations, universal set of gate operation, control not gate operation. And I need to map the positions of quantum walk to the gate operation, right? So now this is an example. This was actually implemented after the algorithm was developed using an ion trap system in University of Maryland. And if you see here, this is the circuit to do gate operations. So implement quantum walk. If I implement 5 steps of quantum walk using gate operations, I get the probability distribution which mimics relativistic equation, Dirac equation. Now what has happened here is my mass and the speed of light, which are like mass is very small, speed of light is very high. But if I change the mass, which means that I'm changing the coin operation parameter, and I can see how the dynamics is going to change if the mass is changed, how my dynamics is going to change if my speed of light is altered, because mass is related to speed of light, and that combinations can be effectively captured and be, very nicely simulated using a quantum walk algorithm. So these are some of the examples which people have been trying to understand the physical system, look at the Hamiltonian or the dynamics of it, or the equation which are describing the dynamics of it, and then see how you can come up with an algorithm which can map to that kind of dynamics. And once the algorithm is there, then come up with quantum circuits to break them down into an implemented form. Once circuits are built, you can implement into, and then you have to optimize. After that, you can implement them into a quantum. Now you can see here, because the ion trap, though it is an ion trap system, if you see the number of gate operations here, there are controlled control not gate, there is controlled control control not gate operations, which has required this large number like 72 qubits, single qubit and 2 qubit gate, and 2 qubit gate operations. So this is R is single qubit gate, and then XX is 32 2 qubit gate operations. So almost like 100 plus gate operations has been implemented just to show a small number of steps of Dirac equation simulation. If the connectivities and ease of implementing this control not gate operations improves, then one can bring down the number of gate operations which is needed. Right? So this, and there's another problem which I discussed in my previous lecture yesterday, where there are chemical complexes, the dynamics on them are also defined by set operations. Now, which also involves environment. Now, if I have to mimic environment, I need to use additional qubit system, right? For 7 particular position space, I would need 3 qubit, but to mimic environment effect, I can take additional qubit and say the influence of those qubits on the real physical, the qubits which mimic the system can be modeled using a 5 qubit system, and one can build a complicated or most involved quantum circuits to mimic the dynamics of what happens in such kind of system. Now why will this help is that sometimes people will measure some output and they don't know what is the dynamics for it, and they have to recover. But if you have a circuit model, then you can actually change the parameters and then see what change in parameter is going to give you an effective result. And the moment you know that, you understand the effect. The moment you have understood the quantum circuit which is mimicking them, which means that you already have a design of such kind of systems. So once you have a design of such a system, you can engineer artificial materials which can mimic the dynamics of that one. So material science and new materials discovery or new chemical complex discovery or new protein ligand discoveries have been explored from quantum computing perspective using these simple examples as a base that you can actually simulate Hamiltonians efficiently and then help us to can help us modeling, right? So there has been a huge class of problems which has been explored at the small scale. I think I tried to give broader, big picture examples of all of them. So there are simulations of fundamental problems. So there were particle-antiparticle generation creation problem, and there was relativistic dynamic simulation problems, which can be demonstrated using smaller number of qubits as in quantum systems. And there was quantum chemistry problems, which we were talking about either FMO complex, or it was nitrogenesis processes, or similar kind of problems. And there are material science problems which we can understand the quantum circuits, or like understand the system's Hamiltonian. And if we can map efficient quantum circuits, I can artificially develop or come up with a model for artificial synthetic material. And people have been trying to see a huge promise in that direction. And the most importantly, the cyber security applications with smaller number of qubits, right? As we showed, 4 qubits, 2 qubits can generate keys without any program or manual interventions. And nature or a quantum wave packets collapse gives you keys, and one can easily generate public and private keys without going into a mathematical complexities which are usually used with it, and nature is giving them as a resource. So these are some of the potential applications of near-term devices. And we know, as we mentioned in the earlier lectures yesterday, if I have a largely accessible, which means that larger number of qubits with high coherence time, then the number of problems one can solve can be huge. And that's just an open ground, right? Because we don't have an access to hardware, and the algorithms have been now developed for various kinds of problems. So there is going to be a lot of scopes for new algorithms, new test grounds, and in fact even new hardware. Though we have been looking at multiple physical systems, you have heard some lectures yesterday, day before yesterday, and also you will be hearing some tomorrow, where all the hardwares have been explored and they are all promising. It's not that one of them is going to be successful and others are going to fail. It can even be that specific hardwares could have specific use cases for next decades, 2 decades, unless somebody comes up with the most, what we call a star candidate, which is going to overcome all the hurdles of all the hardwares and effectively solve the issues which we have. Having said this, try to give a wrap up of my 2 lectures today, and probably will have slightly more time to answer questions like yesterday. Okay, so thank you. So we have questions in.
It's in the Q&A box, Professor.
Yeah, I'm just trying to.
Yeah.
Okay. Can you please throw some light on the superdense coding using cat state? Okay. Now, probably can you please show light on superdense coding use cat state, but somebody may not know what cat states are. So I think cat states are a larger number of qubits, or what we call a macroscopic superposition state is what we can call a larger number of qubit state. But now I think that would involve. Okay, so I think without enough background, I can't explain this here. But what it would say is that you can take a multi-qubit entangled state, or like what we call as a cat state, and then you can encode more number of, or what you can see is that you can actually send larger number of classical information using, for example, if I take n qubit states, I can send, I think, two times n number of classical bits with that, I guess, right? So you can actually communicate more number of, or like, encode more number of classical bits in smaller half the number of quantum states. I think I don't have I need the background to explain this. At this point, I think that's probably is a simple way. What I showed was using a single qubit entangled state. I can encode two classical bits. In a similar way, I can take a 3 qubit entangled state, and I can send some two times of that number of bits, I guess. Yeah. So we can keep on increasing that. So can we make T gates using wave plates? Yes. So I think there is a famous optical tools which we call QHQ plate, and this was long back. It was actually shown by Indian what we call Indian physicists who have been working on optics long back. Professor Sudarshan, Simon, Mukunda, they all came up with a very what we call very simple optical models, combination of quarter wave plates, half wave plate, and quarter wave plate, and you can actually rotate them in some particular configurations, and then you can realize not just T gates, any SU2 operator, what we call, like you can actually transfer the state of photon from one point to any point on a Bloch sphere just by using a combination of QHQ plate. Today this has been actually commercialized as QHQ plate by famous companies, but the foundational idea had come from Indian physicists who had shown in the matrix language, and it was converted into an optical setup later on. So there are ways you can easily do, not just T plate, any T gates or any gate can be realized. Sir, what do you mean when you say that we can't do 2 qubit gate operations? No, what I'm not saying that you can't do. What I'm saying with photonic system is that if I have two photons interact together, and if I want to do 2 qubit gate operations, it means that my 2 qubit gate operation should be able to give me all possible configurations as an output. But bosonic behavior restricts me to get all possible configurations as an output. It only gives me a limited output. So the example would be that if I take a 2 qubit system, my output should be a very generic state. If I have to get a generic, which means that I should get 0, 0, 0, 1, 1, 0, 1, 1 as a possible outputs. But if I am using 2 photons and I try to generate, every time I do, I will only get 0, 0 or 1, 1. I'm not going to get 0, 1 or 1, 0 as an output. So now, which means that the two possibility or like the two states doesn't occur at all. So which means that I'm not getting the access to 4 dimensions or like 4 basis states of a 2 qubit system the moment I make 2 photons interact. That's what I mean when we say this 2 qubit gate operations does not happens with limited behavior. So just to overcome this issue, they have used ancilla additional photons and then manipulated so that you end up getting all the 4 basis states of a 2 qubit system. Okay, how to entangle 2 photons? Okay, so I showed one of the methods which what we call spontaneous parametric down conversion method, SPDC, where you can take 2 photons generated from the same down conversion process, and those 2 photons polarizations can be made indistinguishable and they are entangled. And people have been looking at various other ways. You can take frequencies and you can entangle them by using them with by passing them to interferometers and then gratings. But there are quite a few ways to entangle them. Would adding +1 qubit increase the potential computational power by 2x? Yes, every qubit increases potential of the computation power by 2 times, right? That's what I said yesterday, because it's 2 to the power of n. That's how computation scales up. So every time 1 additional qubit you add, the number of basis states you're going to get doubles, and then your computational power also increases. Yes, sir, for a person wanting to be in quantum computing, will an undergrad major in physics or CS or mathematics will be best? I think this is the question which was also asked yesterday. So you can, whether you are undergrad in major in physics, computer science, or mathematics, you can choose any of these areas, but you have to address the problems from that perspective. If you are coming from a computer science background, you would be more equipped to look at algorithms from a computer science perspective, and with basics of computing, physics, uh, driven work to algorithms and efficient algorithm development. If you are coming from a physics side, then you will be more interested towards simulating complicated physical systems and how quantum computers can help you. So the way you approach problems would vary, but it's these are all like at the interface of different subjects. Just saying that I'm only look at computer science and I don't want to look at any physics model, then you will not be able to approach. If you're a physicist and then if you say I only look at physics, I'm not interested in algorithms, then it will be very difficult. So you need to have some exposure, a small exposure, or like some fraction of exposure to that area from physics side. Then you can always be a computer scientist and do a good work in algorithms part. Right? So can you suggest? Okay, so the one of the most standard textbook in quantum computing has been Nelson and Chuang's Quantum Information and Quantum Computing. Introduction to Quantum Computing by Laflamme Moscow has been another standard textbook which gives you an essence of algorithms. In fact, whatever I've tried to squeeze about algorithms, introductions, they all are covered in the first few chapters, and exercises is going to help you in long run. And these two are standard, and there are many books available now. Something at the elementary level to complicated level, and John Preskill's lecture notes for something which has been from an information theory perspective and quantum computation has been very resourceful for people from physics side, and Laflamme's and Moscow's book Introduction to Quantum Computing has been very handy for people coming from mathematics and computer science background, and Nelson and Chuang's has been handy for people who are coming from physics background. So it means that every book is trying to address from different perspective, but you can go skim through the earlier chapters and you'll figure out which one is most ideal to you depending on the background you have, whether you're physics, mathematics, or computer science. Can the two entangled photons travel through same cable? Sorry if I missed this. So can a two entangled photon travel through same cable? Now the cable, or what you call, two photons, if they are entangled, they can. There's nothing. If they are entangled in polarization and part degree, but they should not interfere. Just because they are in different state, you can actually get them. But how do you measure that? Right? Now that's a problem. So you will not be able to measure two photons which are coming to the same optical fiber. So you can only establish they are entangled if they are spatially separated, or else you will not be able to, and that's a tricky part. I can always send two photons into, but the moment two photons enter, then they might lose even entanglement, right? Because two photons, if some change of the state happens, they would end up interfering. If they are sending two photons which are H and V, they just go as H and V, and if I have a beam splitter, H will go in one path and V will go in one path. I can separate them later on together. But there's an entanglement, then there can be some kind of interference which can happen between them, and measuring them would be very difficult. I'm having a question on how we can implement those solutions in an existing setup. I don't know which solutions you mean, but I guess you are referring to implementing some circuits which were shown in the lecture. So as I already gave some examples of either it's a relativistic dynamics equation, or you are looking at FMA complex. The moment you end up having a circuits in front of you, then people who work on hardware can easily realize that whether these circuits are implementable in the kind of system they have, because they do have a fair idea of the number of gates they can implement, the coherence time of their hardware, and that's how they try to look at it, right? So of course, if you are having some few tens of single qubit gate operations and few tens of 2 qubit gate operations in a circuit, and the problems are that small, you can easily implement them. That's not a big problem. So also how about the reusability of photonic qubits? Is it any better at low temperature? So no, how photons are generated matters. If I am generating photons with an SPDC process, the temperature may not matter explicitly. But reusability, fact, that's not actually not been an issue at all, because photons, if you are generating with a technique like SPDC, which I described in the talk, you can actually generate millions of photons per second. So when I have photons generated in millions, I'm okay to lose them. And problem is that the moment you make a measurement, you are actually destroying them, because photons, once they fall into detector, you are getting that information that photon is converting it into an electrical signal, and you lost the photon and you can't reuse them. But you can always generate millions of them, and that has not at all been an issue with photonic system. Photonic systems issue has only been in efficiently doing gate operations, particularly multi-qubit gate operations. That's not that. Considering that the quantum circuits have thousands of gate operations, if you apply inputs, do we get same output or n number of outputs every time due to quantum operations of superposition and decoherence? Now, okay, this is an interesting problem. Considering quantum circuit having thousands of quantum gates, if you apply inputs, do we get same output or n number of outputs every time due to a quantum properties of superposition or decoherence, or etc. Okay, now let's say decoherence, we'll keep it aside. Let's look at superposition. It completely depends on the problem you're trying to solve. If I know I'm trying to solve a ground state finding problem, which means that ground state will be only one in a given state, which means that after you implement a large complicated circuit, at the end you are going to get only one output every time. So that is your solution, right? Which means that your constrictive interference is concentrated during the circuit operations to your solution. But if the solution itself is a superposition output, then you are going to get different outputs at each time, and when you repeat your experiment few times, you will end up getting the pattern of your probability output. Then you say your solution is a superposition of these possibilities. So it means that you will have multiple solutions to the problem. If I'm looking at a search algorithm, if my solution is one definite solution, you will only get one answer even if I'm running it out 10,000 times. So now decoherence can make it probabilistic, and you will end up getting multiple outputs. So that's where we see the maximum probabilities, and there will always be some noise which is associated with it. But this is an interesting question. If we get different outputs every time, how can we use quantum system? Yeah, that's what I said. The output itself is a solution. If your solution is superposition, you will get solution that's complex as your solution. So for a quantum information processing, whether we can use quantum photonic circuits. So quantum circuits, it's common, but yes, for quantum information processing, photonic circuits has been used. In fact, whole of communications today or cryptography people who talk about are using, and communications does deal with information processing. Photons can travel in position space easily, position or in space. That makes quantum information processing more efficient with photonic qubits and photonic circuits. So I don't think there's any in photonic quantum communication, when a qubit is transmitted to a distance, how it holds its entanglement, and that's the beauty. So if you have an entangled state, if you're sending them across, if you're not making a measurement, they do remain entangled, right? Unless you are having some operations to destroy them. People have demonstrated it to thousands of kilometers. So I don't know how it holds entanglement, because there is, as I also mentioned today, photons don't have okay, let's put it like this. Atoms have their internal energies and they are massive, and they can get influenced by something. And magnetic fields can influence atom because electrons are there. So if I'm using atoms as a qubit, they lose their quantum properties because of external environment. Like photon doesn't have such kind of, that itself is a fundamental particle. So external influence won't affect the state of a photon. That's why the moment I create entanglement, they remain entangled. Now what will happen if you are sending it through an atmosphere where you have water molecules in it and humidity, and this can alter your polarization a little bit, because photons do transmit through them, and polarization get changed, and that will destroy entanglement. So people, when they are done thousands of kilometer experiment, they didn't laterally transfer photon in a free space. They actually transferred it to an atmosphere, because your atmospheric distance is about just 10 kilometers, where photons do lose some kind of their polarization behavior, but not completely. But after it is out of atmosphere, there is nothing. So the states remains unaltered. So a large hundreds of kilometers of travel there. When they come back, they would again have about 10 kilometers of atmosphere. So with just 10 or 20 kilometer of atmosphere, a small some change would have happened, but you can still have them entangled together. But if you are sending it laterally on a free space and say 40-50 kilometers, you might actually lose entanglement very easily, just because the photons polarization states get altered in our atmosphere. So on a balanced operation with more than 2 qubits, with both zeros and ones, like zeros can help without any superposition, I guess. So result should also be palindrome. Maybe I'm wrong, but I didn't understand this question explicitly, but I think I'll come back. So there's been quite a few more questions. Okay, sir, I'm doing MTech in quantum computing, DAPT. We are doing here a single photon based quantum communication. I did photon based lab in my first semester. Okay, this is a very question different. Isn't the variation eigensolver a kind of quantum annealing or vice versa? No, quantum annealing is a very specific approach. Variation eigensolver does look at part of a bit similar to quantum annealing, but it's not only quantum annealing. You can actually have different configurations of operations designed in them. You can even have circuits designed for them, but annealing does not deal with quantum circuits. So you can, it's a very specific purpose of them. So I don't see them, they are all identical or equivalent, but both of them do deal with optimizing or like finding a ground state, but the way they do is different. Variational eigensolver does depend on circuits, and annealing will not need quantum circuit. Continuous versus discrete time. Okay, so there is I didn't go into detail about it, but what continuous time quantum walk would deal with that, you don't have a coin degree of freedom, what you call horizontal vertical. It's like a diffusion model. All that you would need is a graph structure. You have evolution of the Hamiltonian, where a discrete time quantum walk model has more controllability, because depending on the toss of coin, whether it's spin up or like an horizontal vertical polarization, you move to that. So which means that you don't need 2 degrees of freedom to implement continuous time quantum walk, but discrete time quantum walk you need 2 degrees of freedom. And in fact, when in the computation model I described, we take polarization part degree, which is like discrete time quantum walk. Local, okay, lots of learning, and that's different. How to analyze the claims made by industry on building. See, I think there is always a lot of claims which can happen with industries, and there is a lot of claims which can you will read in the newspapers, but there is a standard academic approach which has evolved over decades. Any research community, when we talk about, I can always, for example, I can generate hundreds of photons. It's not difficult for us in our lab to generate hundreds of photons. We can set up them, and then that doesn't mean that I have hundreds of qubits. I can claim I have qubits only if I have done these gate operations, and then I've demonstrated them as by creating a density matrix, what we call a tomography. I need to implement 2 qubit gates and prove that this is repeatable with so and so fidelity. Only then your qubits claim are addressed. I think when there's something which one has to, as people who are close to the field, when we are trying to evaluate the claims, it has to be based on the results which are come out as a test of it. So I can, for example, I can always configure hundreds of superconducting qubits chip, right? I can always design, give it a foundry, and I can get the chips. But that does not mean much for a computation, right? I need to take those chips, I need to make them work. I should connect them all and then test every qubit's gate operations fidelity. And sometimes when the design is done or when it is fabricated, many of them may not work the way you want, which means that it has happened everywhere. I gave an example of Google's, which they had 54 qubit. When they did the test, not all qubits would have same fidelities, not all qubits. But then one of them was actually had completely failed. And in fact, that is also the best of their qubits, also best of their chip, right? So there can always be all these configurations. The most, at least from an academic point of view, we always try to get it peer reviewed, published, and then that's how you establish the claims of a qubit. It has to be a tomography or some density matrix reconstruction. Right? So, sir, applications in medical and healthcare, there is the whole pharma industry is waiting for an efficient quantum computers so that you can come up with the most optimal or a rational form for drug discovery and material science development. So there is huge scope in that direction. So can cat state be used for QKD? Yes, I mean you can use any state. I mean the moment you are generating a multi-qubit quantum state, you can always use for any of them for communication and cryptography. You need to come up with efficient way of using them. That's all. So what software should we use for simulation? So see, simulations, there are no softwares. These are like codes, right? You can write your own Python code. There is Quizquit available from IBM. The CDAC Bangalore had developed a program, and today they have QNeos also available, which actually simulates the circuits for different hardware, which has been developed in India. So there are quite a few simulators available for that. What are the current fabrication techniques and synthesis process we are using to create quantum materials relevant to quantum computers? Okay, so people, photonic systems, there has been for superconducting systems, the foundries have been used for spin qubit systems. People have been using. I'm not familiar with the material science side of it to throw more light on it. What kind of techniques? But with the photonics one, most of its wafers on which waveguides are being used efficiently, and one can design waveguides and then controlled operations on them, and that's been something which has been used for photonics in a chip. Okay, if the interest is to explore opportunities in quantum-inspired algorithms to run on commodity hardware, solving industry optimization, people have already been looking at quantum-inspired algorithms. It has happened. There's always development which has come, like this is correlated randomness, and there is quite a few quantum-inspired algorithm people have tried to look at. But industrial optimization problems is something which annealers have been effectively used today, and people have been looking at them. What mathematical and quantum topics are prerequisite. So I think the basics of how quantum states are generated and evolved, understanding of controllability of superposition interference becomes very, very important to develop algorithms and then to engineer them for your design, and that's what I would say is a prerequisite. Okay, so I think tried to complete all the questions which were here.
Yeah. Thank you, Professor. Thanks a lot.
Thank you very much.
Thank you, Professor. Have a good day.
I hope you didn't miss the earlier low voice was not very bad, and I hope it was still okay.
No, it was fine.
Okay.
Probably you are just slight away from the mic, I guess. That's it.
Yeah, that's what I realized. Okay.
Fine, Professor. Yeah. Thank you, Professor. Thanks a lot. Thank you, all the participants. Have a good day. Bye.
Thanks to all.
The recording has stopped.